All right, Algebra 2, here we get rolling into Chapter 4, which really, for as much fun as the couple chapters we've done at the beginning of the year have been, this is really the first chapter of the year where we really start diving into some true Algebra 2 material. Most of what we've done so far has really been a review of content that you had in Algebra 1, and they've mostly dealt with linear functions. But now, for the first time here, we start getting into what we call non-linear functions, which means functions that when we graph are not going to make a straight line. And that's where we're going to spend, pretty much the rest of the year in Algebra 2. And it's where most of higher end mathematics lives, dealing with nonlinear functions. So, Chapter 4 and Chapter 5 go together, dealing with what we call nonlinear polynomial functions. And what we're going to start talking about here exclusively in Chapter 4 are quadratic functions. So it's a phrase we might not know very well just yet, but it's one we better know pretty soon because we're going to spend all chapter working on it. So the simple definition of a quadratic function is this right here. It's a second degree polynomial. And I've realized now I didn't really have anything in the notes here describing what all of that means. So I want to make a couple of lists right here, and what you can write this down or not, but I want to make a quick list right here of polynomial functions and then compare that to a couple of non-polynomial functions. And it's just so you guys can see side by side what it is that those ones look like. And within this polynomial, I'm going to break that one down a little bit further into a function. And then I want to talk about the degree of a polynomial as well. This is really a pretty simple concept, guys, once you get the hang of it. Well, first of all, a polynomial function could be something really simple like, and since we're doing it as a function, we usually say f of x, it could just be a single number, a constant like 5. And in that case, we would say, I'll tell you what, I'll come back to degree in a second. Then there are linear functions like we've spent the last couple chapters talking about, something like 2x minus 3. Those are two functions that hopefully you guys already know how to graph. Now things start to get more interesting though when we start getting into this chapter, because now your polynomial functions might be more advanced. They might contain exponents like x squared plus 3x minus 7. That's just an example. And later on in still the first semester, we're going to get to even more complicated polynomial functions that might look something like, and I'm just guessing here, making some stuff up, how about negative 1/2 x to the 4th plus 3x cubed minus 7x plus 1. Those are all examples of types of polynomial functions. And what makes them polynomials is they all have x used as the base of an exponent and then an integer for their exponent. So real quickly, that first example I came up with, f of x is equal to 5, has no x's in it at all. We would say that's a 0-degree polynomial, which is really just called a constant. The functions we have been dealing the most with on this second line, 2x minus 3, remember guys that when there is no exponent written there, that's really a 1. So that's what we call a first degree polynomial, and that is called a linear function. Now, here's the kicker though, guys. This is what we're going to spend all of Chapter 4 dealing with. We have an x there with an exponent of 2. That's what we call a second degree polynomial, and that is what we mean by a quadratic function. And once we get into Chapter 5 in a while, then we start looking at some of these more complicated polynomial functions. This one is a 4th degree polynomial, and the name for that, you don't need to know this right now, it's called a quartic function. So all of those are types of polynomial functions. Now, non-polynomials over here on the right, a lot of this isn't going to make a whole lot of sense, guys, because you haven't done much, if anything, before with non-polynomial functions. But if you ever put an x on the bottom of a function, that one right there is a non-polynomial. This one is what we call a rational function. If you ever had something like g of x is equal to the square root of x plus 3, a square root is a non-polynomial. Later on in the year, you're going to learn about weird things called exponential functions. or something called logarithmic functions. This would be the natural log of x. And then there's going to be trigonometric functions later on in the year, like g of x is equal to the tangent of x. All of those would be examples of non-polynomials, but I'm getting ahead of myself. We're focusing now in Chapter 4 on polynomials, and specifically this type right here. So if I go back, this is what we mean by a quadratic function. It's a second-degree polynomial. So now in red, let's go ahead and write down what it is. And remember, you can use either function notation here, f of x, or we can use a y. They really mean kind of the same thing. Either one of those will be equal to, and now here's the generic way that we contain or that we write a polynomial quadratic function. A multiplied by x squared plus b multiplied by x, and then a plus c at the end of all that. So that is the definition right there, everybody, of what a quadratic function really looks like. Ax squared plus bx plus c. And this one I wrote here is in something called standard form, but don't bother writing that down because we're going to do more with it here a little bit later on in these notes right here. So in this case, let's pay attention here, guys. X is the variable. So your variable x is being squared in the first term. Then there's usually what we call a linear x term in the second term. And then at the very end, there's a c. Now that c stands for constant. It contains no x. So you have like a plus 3 or a minus 7 at the end of that function. So that, everybody, is what a quadratic function looks like, at least in standard form. And I have got a long list here. This is going to be a little bit scary when you see it here, guys, of a whole bunch of stuff that we're going to talk about with each quadratic function. Every one of them follows some of these patterns. So let's buckle in here. It's going to take us a minute to get through this, but all of this is really important information. The first thing we're going to talk about, the shape of a quadratic function. Okay, and I tell you what, rather than just make this list right here, I actually want to dive into our first example here. Wait a minute. There we go. And see if we can't get a sense for this on our own here. Now, what I'm going to say right here is really important here, guys, so please pay attention. All year long, we're going to learn about one new style of function after another. This is just an example of a list of what all of those might look like. And every time we learn something new, you guys aren't going to know what the shape of that graph looks like. But the one method that we can always fall back on to learn something new about a graph that we're not familiar with is this method that you guys learned back in the day, probably in 6th or 7th grade. We're just going to make a table of values. Now, one of the things I'm hoping you guys remember coming out of Chapter 3 now is that a two-variable equation such as this has an infinite number of solutions. So I can't ask you to come up with all of the solutions and write them out because there's too many. But what we can do here is find some, plot them, and see if we can't figure out a pattern. Now, how many do we need to find? That's the important question. And the silly answer is enough. Just enough to get a sense for what the shape of this graph looks like. So what's always a good idea is to start with integers here, and 0 is usually a pretty good one, and then a 1 and a 2, and I'm going to put a 3. Now, x in a function like this is what we call our independent variable, meaning x is independent of y. We can let x be anything we want it to be, but y is the dependent variable. Its value depends on the value we chose for x. So here we go. Our first value here is to let x equal 0. So we're going to take 0 and then square it. And of course, that means 0 times 0, and we end up with 0. For y. So 0, 0 is our first solution to this particular two-variable equation. So we go ahead and plot it, and then I ask you a really dumb question. Do you now know what this graph looks like? And the answer is, of course not. You never know after just 1 point. So we keep going. Now we're going to let x equal 1, and 1 squared, 1 times 1, is 1. So we just came up with the solution 1, 1, and we'll plot that as well. Now do you know what it looks like? No, you don't. After 2 points, everything looks like a line, guys. But you got to dig a little bit further, and here's where things start to get interesting. When we put in a 2, we take 2 squared, and we end up with 4. And when I plot the point 2, 4, now all of a sudden we realize something very important here. If you'll notice, these 3 points are not collinear. And that means, for the first time all year, we're dealing with a non-linear function. I take that back. We did graph some absolute value v's back at the end of Chapter 2. Those were technically non-linear as well, although they were made up of 2 rays. And let me do one more point here, guys. When we plug in 3 and square it, we end up with 9. And I think that'll just barely fit on my graph here. 3 to the right and 9 units up, I believe, is going to get us right there. Now, we certainly could go further. We could put in a 4 and a 7 and a 12 and a 39, but nobody's got the time to graph these numbers that I'm coming up with right here. 39 squared, 1,521, I think. Anyway, the point is, nobody has room or time to graph those points right there. So at this point, we're going to kind of extrapolate, everybody, and say, all right, what's going on the right-hand side? It kind of looks like this function is increasing, but at an increasing rate, and it's kind of curved up here, and it looks something like that. Now, I'll tell you more about that shape in just a second, but that's pretty good. Now, the other thing you have to consider, though, is here, everybody, the domain, the x values that you can put in here to a quadratic function. We've put in 0, 1, 2, and 3, but you can also put negative numbers in there. And this is where quadratic functions start to get interesting. So now I'm going to put in -1, -2, -3, and let's see what happens. So here we go. We're going to take -1 and put that in for x and square it. And you're better off using your head here than using your calculator. -1 squared means -1 times -1, which equals +1. So we just came up with a fifth solution now of -1, +1. Okay, and now we're starting to see, I think, what this graph is going to begin to look like. When you put in a -2 and square it, -2 times -2 is +4. So -2, +4 gives us a solution right there. -3 squared is +9. So 3 to the left and then 9 units up. And now we're starting to get a really good sense for what this graph looks like. It's curving upwards on both sides, and it takes this particular shape right here. And this shape, everybody, let's go ahead and write this word down. This shape is called, maybe you know this word and maybe you don't, it's called a parabola. That's how you pronounce that, a parabola. And anytime you throw a ball up in the air and then it comes back down to the ground, it takes the shape of a parabola. When you go to a water fountain, back when we had water fountains, and they shoot water up and then back down into the drain, it takes the shape of a parabola. A lot of microphones on the sidelines of NFL games where they're trying to capture sound are called parabolic microphones because they're in this general shape here as well. So a parabola is a word that we need to know. That's the shape of every quadratic function. So hopefully you guys left yourself some room here. The shape of every quadratic function is a parabola, so we're going to go ahead and write that word there. And every single, so okay, we covered that one. Every single parabola that we're going to deal with in this chapter either opens up or it opens down. And this, and in fact, a lot of things we're going to talk about with parabolas, falls right in line with what we talked about with absolute value V graphs back in Chapter 2. It's amazing how many things these have in common. Just like with those absolute value V graphs, it's your A value right here, guys, that determines whether that parabola opens up or down. And so the determining factor here is your parabola opens up if your A value is greater than 0, meaning that A is positive, or it opens down if A is less than 0. So that's an important thing to know, and we'll play around with that a little bit more. Now, the curious among you might have noticed something. It opens up if A is positive. It opens down if A is negative. There's a third possibility. A could be positive or negative. What if A is equal to 0 itself? Well, in that case, guys, if A is 0, this entire term right here drops out completely because it's 0 times anything squared. This is all you're left with. and bx plus c isn't a quadratic function, that one right there would just be a linear function. It's a line, and so it doesn't open up or down. And that's why we have this little note right here that I didn't mention until just now. A quadratic function has to contain an x squared, and what I really mean by that is a cannot equal 0, because if a were to be 0, you wouldn't have a quadratic function, you would have a linear function. Okay, let me get rid of a lot of this junk, and we'll get back to where we were. Okay, so those are two important things to know. A positive a makes your parabola open up, and a negative a makes your parabola open down. Okay. Every parabola out there has what I call, and this is a word that I'll use once in a while here kind of as a joke, the word is girth, okay? How wide or skinny or normal your parabola is. Now those words don't mean a whole lot to you just yet, but the more we deal with this and the more examples you see, you guys will start to know what I mean. I don't like the order I wrote this. A quote-unquote, in fact, let me put air quotes around that, normal parabola is one that has an absolute value of your a equaling 1. And what I mean by that is a can be either positive 1 or negative 1 for your parabola to be quote-unquote normal. And as I said, you'll get a sense for what a normal parabola looks like, but for now I'll just draw it real quickly like that. Now, the next two things go back to what we talked about in section 2.6 with the transformations of functions. If, which way do I want to do this? If the absolute value of a for you is greater than 1, meaning if you start this function off with a 2 or a 3 out in front, what that's going to do is it's going to stretch your parabola vertically and it's going to make it taller. And when something gets taller, that gives it the appearance of being skinny. So a skinny parabola might look something like that. Now again, it's tempting to think that that one is getting compressed horizontally, like it's being pushed in on both sides, but that's really not what's happening. It's actually being stretched vertically like this. It becomes taller, it just appears skinnier. And the other end of this, guys, what would make a parabola wider, well, it's actually making it shorter. That's what will happen when the absolute value of a is less than 1. So that's when you might end up with this nice wide-looking parabola that looks something like this. And what's happening here is the graph is actually being compressed downward. All right? It makes it shorter, which gives it the impression of being wider. Okay. Despite my very bad writing, what I tried to write here is that every particular graph of a parabola here is symmetrical. And it's got symmetry about, this is a really dumb thing to say, about its axis of symmetry. So think about how obvious that is. It is symmetrical about its axis of symmetry. If I go back to this graph, that we had just a second ago here, guys, the line of symmetry of this graph would be this vertical line that goes right down the middle that you could fold this thing down and the left and the right side should match up perfectly if we drew this correctly. And I think you guys can see this point maps over here to this one. That guy maps to that one, that guy maps to that one, and this one is on the axis of symmetry. It just kind of maps to itself. And later on in, let's see, the next section of notes, 4.2, we're going to learn how to find that axis of symmetry, but for now, we're not too concerned about it just yet. Got that? And last thing we need to fill in now, every parabola. All right, let's see, why did I change that? There we go. So we talked about symmetry, we talked about, and here we go, last one. Every parabola has either a maximum value or a minimum value located at its, let's think about that. Maximum, everybody. When we're talking about a maximum value, we mean a maximum y value. That really means that we are dealing with a highest point. Or in some cases, if we're dealing with a parabola with a minimum value, that's what we consider to be its lowest point. And going back to the parabola that we graphed already, that didn't work. This one here, guys, that's what I needed to do. Since this is a parabola that opens upward, this one has a minimum value right there. That point I just put a red box around is the lowest point on this graph. it doesn't have a highest point because the arrows tell me that this thing continues to get higher and higher in both directions as I move to both the left and the right. So this parabola, in this example, has a minimum value. And where does that occur? At this point right here, which, let me get rid of some of the junk right here and let's label that. This point right here is a word we've heard before. That's called the vertex of your parabola. Again, we talked about a vertex when we were doing absolute value v's. Back in chapter 2, same thing is happening here. So back to this list, here we go, guys. A function has either a maximum value if it opens downward. Okay, a downward opening parabola would look like this, and then that point right there is the highest point on this curve. Or it can have a minimum value if your parabola opens upward. Okay, and that's what we just drew a second ago. There would be your minimum value, but in either case, that maximum or minimum occurs at what we call the vertex of your parabola. So that is a word that if you didn't learn from chapter 2, the vertex is where the two rays of your absolute value graph came together, we absolutely need to know that definition here within the context of chapter 4. All right, guys, so that's a lot of vocab and a lot of stuff to throw at you right here. Once you get into it, it's maybe not that bad. So let's take a look at what we can do here together. So we went ahead and we graphed our first parabola here, and it looked like, okay, I broke it. There it is. It looked like this. Now, this, everybody, is an important graph, and we want to make sure that we have this one down. This graph is the graph that which all other parabola graphs that we're going to come up with are going to be based off of. So I want to make a note right here, guys, and I want you to put this in your notes that this graph right here is what we call the parent graph for all other parabolas. Okay, all quadratic functions that we're going to draw are going to require us to know that this is what the most quote-unquote normal graph out there looks like for a quadratic function. And now everything else, as I said, is going to be based off of that. I did want to show you guys one thing before we go too much further, though. Your graphing calculators are really, really useful for coming up with graphs of nonlinear functions. And unfortunately, guys, I thought I had, but I don't, an app for the TI-84. So I'm doing this on this Desmos calculator, which is web-based. You guys can do this on your Chromebook or your phone or anything like that, but your 84 would work here as well. You guys have a Y equals button in the upper left-hand corner of your keypad. If you were to hit that, you'd get right here. And I'm going to go ahead and type this in just so you can see what this looks like when a calculator or a computer does it really, really nicely. So there's y equals x, and now I'm going to hit this a squared button, and there it is, guys. And let me go ahead and hit enter now. That is what a computer graph of y equals x squared looks like. And with Desmos, this is really nice. I can just kind of move it around with my fingers the way you guys are used to doing with a phone or an iPad or sometimes even your touch screen there too. And you can see that's kind of the general shape of what a parabola looks like. We'll play around with the calculators a little bit more this year. Okay, what else did I want to write down right here, guys? Okay, now seems like a decent time to talk about this. Forms of quadratic functions. There are 3 of them that are most common, but I think your book really only deals with 2. If I'm not mistaken. Yeah, I didn't even put the 3rd one in here, so I guess you guys are off the hook. Standard form, everybody, is what I wrote down back on the first slide. F of x is equal to ax squared plus bx and a plus c. The other name for this that you'll hear me use from time to time is also called expanded form. And the reason for that is because this particular algebraic expression right here, ax squared plus bx plus c, is in what we call expanded form. There are no parentheses. There's no factoring going on here. Now that's in contrast, though, to what we're going to talk about right here, which is called vertex form. And vertex form looks more confusing at first, but is actually a lot more useful to us than standard form. Vertex form starts with this value a, just like standard form did, but now in parentheses, we're going to have this, x minus h as a binomial. Close it and square it, and then we're going to put a plus k at the end of all that. That, everybody, is vertex form. Now, before we move off this page, I want to give you just a little bit of extra info right here, guys. A is everything that we talked about back over here on the first slide. So, wow, that tells us a lot. Right here, A tells us what direction our parabola opens, up if A is positive, down if A is negative, and it also tells us the girth of our parabola. If A is 1 or -1, it's normal. If the absolute value of A is less than 1, it's a wide parabola. And if the absolute value of A is greater than 1, then it's a skinny parabola. All of that information we get from A, and that works. Oh, something moved on me right there. And that works, everybody, regardless of which form we're talking about here. You know what? I bet if I had moved this, yeah, that would have worked a little bit better. Okay. So that's where we were. So what do I want to have you guys jot down right here once I fix where this slide is located? Okay, so that kind of tells you what the A is useful for. The only other thing that's useful here is that C, this number that's added at the very end, that's the y-intercept of your parabola. And you guys got a pretty good understanding of what a y-intercept is back when we were doing lines in Chapter 2 and Chapter 3, still applies here as well. That, though, you guys, is all we're going to say about standard form for right now. In our next section, 4.2, we'll talk about the significance of this b value here, but I think at this point that would just kind of confuse you. But good news for you guys is, I know it doesn't seem like it at first, we're going to spend the rest of our time here in 4.1 dealing with vertex form. So for this section here, in fact, let me go ahead and write that. 4.1 from here on out mostly deals with vertex form, whereas standard form is what we're going to cover in section 4.2. So, in vertex form, here's our equation. F of x is equal to a times x minus h quantity squared plus k, and everything we talked about with a before still applies. A tells you what direction this thing opens and how wide it is. But there's two important, really just one more now, important piece of information. The vertex of your parabola is located at the ordered pair h, k. And I don't think that using those letters really sank in with you guys when we were doing our absolute value v graphs back in Chapter 2, but they better start sinking in now because we're going to see these same two variables, h and k, throughout the year in almost every one of these styles of functions that we're going to be dealing with here throughout the rest of the year in Algebra 2. So we really need to understand that h and k are pretty important values. Now, just to make sure we understand what's going on, h is the number right here that's being subtracted from x inside the parentheses. K, though, is the number that's being added, not subtracted, but added at the very end of the function. So that's an explanation of it. I don't think you're really going to get it until we dive in and do a couple of examples. So I've got a few that I'm going to run through with you here, guys, and we're going to try to graph all these out and try to see what vertex form can actually be useful for. But I think now's probably a pretty good time to wrap up this video, so I'm going to stop this one, and then we'll pick up the next one in just a moment here.